Okay, so let's just review what we had done last week a bit. If you remember, we were having, okay, you had this, we were studying the Lagrangian, which turned out to be the Klein-Gordon Lagrangian. This is our the Klein-Gordon equation, which describes essentially relativistic spin zero particles. So why do we know it's relativistic? Because we can also obtain it from this E squared is equal to P squared plus M squared relativistic energy expression. So that's the prediction of the Klein-Gordon equation. And then we had this quantization condition. Once we have the Lagrangian, we can obtain the corresponding canonical momentum. And this was our quantization condition, that the momentum and the coordinate conjugate pairs, their commutators should be, their equal time commutators should be zero unless they are at the same point. Now this is also related with causality in the sense that these commutators, remember, if you consider these operators as, I mean, since we are looking at a real field, these operators correspond to some observables. And two observables at space-time separated points, they shouldn't be influencing each other, so they should commute. And then we say we were looking at the various pictures. We have the Schrödinger picture, the Heisenberg picture, where the operators are time-dependent, not the states. So we will be mainly working with in fact, none of them. We will be eventually working with what we call the interaction picture. But for the time being, let's say that we are working in the Heisenberg picture so that the operators are also time-dependent. And what we did was, okay, since the reason why I'm saying that we are doing in this time-dependent operators is the momentum is the time derivative. So either you can say that, okay, the momentum is completely independent parameter, this phi that has nothing to do with the derivative of phi, and just continue working, or say that we are in the Heisenberg picture, so phi that is actually the time derivative. And then we know the Hamiltonian. Okay, so what we had done, eventually we were looking at the commutators. Okay, we expanded our fields. In terms of, well, this was one of the possible expansions. You see, to start with, we only had the 1/2e here at the beginning. But then just by changing the normalization of these operators, phi k, for the positive frequency part and the negative frequency part, we said that, okay, let's convert it to square root of 2EP. It's just a change in the normalization. The advantage of this normalization is that these phi operators turned out to be just like the commutators, is just proportional to Dirac delta with no additional factors of E, etc. E in the sense of energy. Now these phi operators, we looked at their commutator with the Hamiltonian, and this phi dagger essentially increased the energy of the state by the corresponding Ek, which we identified as the energy, and the phi dagger, and the phi just decreased it by Ek. And this was the Hamiltonian in terms of these normalized phi operators. So you see, if you look at here, I mean, this is just the number operator, this phi dagger phi. It just counts the number of particles that have a momentum p. And this EP is the energy of the particles that have momentum p. So basically what we are doing here is multiplying the energy with the number of particles having that energy and summing over all possible particle momenta. So in that sense also, this expression of the Hamiltonian makes more sense. And then what else we did? Okay, that was where we had left. Now, we identified this k as the momentum of these particles, but we didn't yet prove it. But the question is, if we want to prove that, the first question we have to answer is, what is the momentum? How can we write the momentum in terms of these new operators that we had written down? Okay, let me just write down the expression also over here. Phi of x is d cubed p over 2 pi cubed, 1 over square root of 2EP, and then we had the phi of p e to power minus I px plus phi dagger of p e to power plus I px. And these px are the product of four vectors. P0 x0 minus p dot x. And P0 in this expression is just EP, which we defined as the square root of P squared plus M squared. And we had our Lagrangian, which was written in this form, 1 over 2 del mu phi of x, del mu phi squared minus 1 over 2 m squared phi squared. And phi dagger is actually phi. And this one we can call the Lagrangian density. Well, it's a density because its space integral gives us the Lagrangian of the system. In that sense, it's the density. And I will treat the Lagrangian density as a function of phi and del mu phi. Of course, when I'm writing it in this form, I will be treating phi and del mu phi as if they are independent quantities. Now, if you remember, we had derived the equations of motion. Now, to derive the equations of motion, what we had said was, okay, the derivative of the Lagrangian with respect to phi dot at the point, let's say, y, minus the time derivative of this one, minus the derivative of the Lagrangian with respect to phi. This is equal to 0. This gives us the equations of motion. Now, another way of writing exactly the same equation is like this. The derivative, yes. Well, you see, here what we assume is that the Lagrangian is a function of phi dot and phi, because that is how we do in classical physics. But then you can say, okay, if you look at our Lagrangian, it depends on phi dot and also the position derivatives of phi. But then we will say that, okay, the position derivatives, always keep in your mind the discrete case. The position derivatives are nothing but the differences of coordinates, of different generalized coordinates, that is the derivatives. And okay, we can just go over it once more. If I take the derivative of the Lagrangian with respect to phi dot, let's say at the point y, this is just the derivative with respect to phi dot of y of d cubed x 1 over 2 del 0 phi squared. Because here the only phi dot term appears over here, and this just gives me d cubed x. The 2 from the exponent comes down, so it cancels 1 over 2, so we have del 0 phi, or phi, just phi dot, times the derivative of phi dot at the point x with respect to phi dot at the point y, but this is just the Dirac delta x minus y. So this is just phi dot of y. And then we said, okay, let's look at the derivative of the Lagrangian with respect to phi of y. This is equal to this expression of, okay, let me just keep the terms that will give non-zero in the Lagrangian, d cubed x minus gradient of phi squared minus m squared phi squared. Now what I will do is the derivative with respect to phi of gradient of phi of x. You see this again keep in mind, this gradient is the difference of generalized coordinates in discrete case. When I take the difference of generalized coordinates with respect to another generalized coordinates, I can just reverse them around. I can first take the derivative with respect to the generalized coordinates and then take the difference. But that basically tells me that this is just this expression. So if I put it back, the derivative of the Lagrangian with respect to phi y is actually, let me just take the derivative. I have minus, here we have factors of 2, minus the gradient of phi, gradient of the Dirac delta of x minus y, minus m squared phi Dirac delta of x minus y. Now I can take the, well, in the first term I need to take the integration by parts. In the second term I can just use the Dirac delta directly to evaluate the integral, and this becomes Laplacian of phi minus m squared phi. So of course this approach just borrows what we know from classical physics. And just combining the previous result, this one, with this last result, it just gives us that d by dt of phi dot and minus Laplacian of phi minus m squared phi, this is equal to 0. Or the second derivative with respect to time minus the gradient of phi, Laplacian of phi plus m squared phi is equal to 0. I'm sorry. And this is what we call the box operator. This is what we had done before. Now, of course, one thing I would like to insist is that it depends. You see, these equations, even this equation, we derive this equation by assuming, to start with, that phi and phi dot are independent. We define them to be independent, and then we can derive this equation. Well, I can also start from saying that, okay, phi and all the derivatives of phi are independent from each other. I can derive a similar equation, and that equation will just tell me that the del by del x mu, derivative of the Lagrangian density with respect to del mu x, del mu phi, minus del L over del phi, this is equal to 0. Well, how can I obtain that? Well, let's look at this one. Well, I can write that as, if I want to treat the phi and space derivatives of phi as independent, well, that I also can do. In that case, what this derivative will tell me, you see, in writing this equation, I started by saying that time derivative of phi and phi itself is independent. So that is the assumption under which that equation is correct. If I change my assumption, say that phi and all the derivatives should be independent, then I should replace this by derivative of the Lagrangian with respect to del mu phi, and del mu phi with respect to del phi, plus del L by del phi. You see, this one over here, this derivative over on the left-hand side, and the same looking derivative on the right hand side, they will be different. The derivative on the left hand side assumes that here phi dot is constant. I'm taking that derivative assuming that only phi dot is constant. The derivative on the right hand side, on the other hand, this derivative is the derivative when all the derivatives, del mu phi, is constant. Let me just make one correction. Here there is not del mu, it's del I, only the space components. Now, if you put it in the Lagrangian and do an integration by part, what you will use is this. The first term actually becomes sorry. This is del I derivative of del I of phi. If you do an integration by part, it will become del I of derivative of L with respect to del I of phi times derivative of phi with respect to phi plus derivative with respect to I of del L over del, this is del I of phi, derivative of phi with respect to phi, plus del L over del phi, where all del mu phi are constant. Well, just keep in mind that L contains an integral of the Lagrangian density. All of these derivatives you should actually be doing inside that integral. So this will just give you a boundary term which will not contribute at all. If you, this will just result in d cubed x del by del t of del L by del phi dot minus del over del xi del L by del x del I of phi minus derivative of L with respect to phi. Dirac delta x minus y is equal to 0. And this is actually this equation over there. So okay, this was the kind of a hand-wavy argument to show that those two expressions are in fact identical. Well, just fill in the gaps and do all the formal steps that are correct formally. So you see, the equation you have depends on under which assumptions you are driving that equation. In fact, another part of the the homework will be just take the action and look at its variation with respect to phi. Well, here you will not be assuming the derivatives are independent of your function. So derivative of any derivative of phi will be actually the derivative of the derivative of well, okay. So that you will make this as this approximation and then show that actually this equation is also enough to obtain this equation, whichever one you like. So if you ask me, okay, should we treat the phi and the phi derivatives as independent? My answer can be yes or no. It depends. Which equation do you want to use? What were the assumptions in driving that equation? If in the derivation of that equation you already assume that the phi and its derivatives are independent, so then you should assume then phi and its derivatives are independent. If that equation is derived assuming that the derivatives and phi, they are dependent on each other, then when you are using that equation, you should make the same assumption. The important thing is that you should be consistent. Okay, so let's continue. Okay, let me ask you one. Okay, any questions up to here? I mean, this was basically a review.
Şimdi phi derivatifin işte independent olduğunu assumption yapıyoruz.
Hı hı.
Ama bu sisteme bağlı değil mi yani? Yani bizim assumption'ımız bunu değiştirmez mi?
You see, what depends on your assumption is the equation you. Okay, so let me look at give you these answers. D by dt del L by derivative of L with respect to phi y minus phi dot of y minus del L by derivative of phi y. This is equal to 0. Okay. So if you want to use this equation, first thing you should pay attention to is what are the assumptions in driving this equation? Well, the assumption was phi and phi that are independent variables. That's it. So the position derivatives of phi should depend on phi. You cannot just assume that the position derivatives are independent of phi or phi dot, because this equation, first of all, started by assuming that phi and phi dot are independent, and it also assumed that there are no other independent variables in your problem. So if you want to use this equation, you have to assume that phi and phi dot are dependent. No, phi and phi derivatives, space derivatives, should be dependent if you want to use this equation. What is the final equation you get? Equals 0. This is the equation you obtain. Or I can say that I can start by assuming that phi and all the derivatives are independent. Then this will be the equation I will obtain. This will be the equation I obtain. And in the case of the Klein-Gordon, okay, if I want to use this expression, I should assume that phi and all its derivatives are independent of each other. And this equation gives me or I can also use this equation. If I want to use this equation, I am assuming that S depends on phi and everything else depends on phi. And guess what? This equation also gives me this equation of motion. You see, if I change my assumption, the way the equation looks changes. But if I am consistent, at the end of the day, the equation of motion that I obtain will all be the same. As you said, my assumption doesn't really change anything, as long as I am consistent in my assumption. You cannot just say that, okay, phi and the position derivatives are independent, and then go ahead and use this first line, the equation in the first line over here. You just cannot use it, because you are not consistent in your assumptions. What do you mean by phase space?
Yani burada sonuçta paydatlar momentum, paylar yine bir şeye denk geliyor. General coordinate'e denk geliyor. Ama daha sonra termül payla payı da ayırdığımız için birbirinden fazlayımızın yapısı değişmiyor.
Well, I didn't define a phase space yet. If you want to define a phase, I mean, you say, if you want to just use the phase space that we define in classical physics, well, you should stick with this one. Now, if you would like to use the second line, how do you define a phase space? Again, the issue is consistency. The important thing is that you should be consistent in what you do. The classical phase space, as you pointed out, it depends on the coordinate and momentum, and that's all you have. You don't have anything else. Well, it is this one, the first line. In the second line, well, you cannot, if you want to define a phase space, you should better define more than one momenta corresponding to one coordinate. Well, would that be a consistent description in phase space? I don't know. But you have to be consistent. Now, let me ask you one question. We have been talking about generalized momentum. What about linear momentum? What is a linear momentum? Okay, we kind of have an idea about the energy. We said that the energy is the energy eigenvalues of the Hamiltonian. But what about momentum?
Amount of motion.
What does that mean?
That means the thing in motion has momentum, and if it increases velocity, its momentum increases. If it increases mass, its momentum increases.
Oh, so okay, you are saying that the momentum is m squared v cubed. But this satisfies your description. If m is increases, this increases. If v increases, this increases. So what is momentum? Or in special theory of relativity, we define the momentum as mv over square root of 1 minus v squared over c squared. Why? So again, I will be asking the question, what is momentum?
Conserved quantity understood translation.
Exactly. Momentum, let's ignore the translation for the time being, but momentum is a conserved vectorial quantity. That is the defining property of momentum. And thanks to Noether's theorem, we can add one more to it. Momentum is the conserved quantity corresponding to the translational symmetry of the problem. Okay, so there are lots of big words over here. What do they mean? So let's start with, what is translational symmetry?
Under translation, my equations of motions are constant.
What do you mean under translation?
So if I have the generalized coordinate phi x, if I vary it to phi x plus delta phi x,
So you are saying that phi x going into phi x plus delta.
yeah, it's the same.
The equations of motion.
I think he's meaning
should be the same. Well, let's see. I mean, we have the Klein-Gordon equation. Let's see if the Klein-Gordon equation satisfies this. This is our Klein-Gordon equations of motion. Let me shift phi by phi plus delta. This will be plus m squared delta equals 0. So our equations of motion did change. Our equation of motion is not invariant under this symmetry. Unless m is equal to 0. So if you want such a symmetry, your field should be massless.
Phi x goes to phi of x plus delta.
Do you agree? Well, when we are, okay, this is a translational symmetry itself also, but not of space. This is the translation in of the field. So here what we are talking about is the translational symmetry in space. Well, you can have two different points of view if you like. You see, whenever we are talking about the coordinates, we pick up an axis, we choose an axis, we choose an origin. And the choice of our origin should not change anything. So as your friend pointed out, our assumptions or our definitions should not change anything. So just translating the axis shouldn't change anything. But if I shift my origin by minus delta, let's look at it like this. So this is my initial origin, initial axis. Let's say I shift my axis by delta, or you can even shift your time. So any point over here, let's say if it has a point if it corresponds to a point R and T in the XY frame, if I shift my axis, it has the it will have the new coordinate R minus RT minus delta. This is R prime T prime. So our new fields in the new coordinates will actually be phi evaluated at R plus delta. And the only thing we did was just change our coordinate axis. And nature doesn't care about our choices. So whatever theory we write, it should be symmetrical under this translation. Now, another point of view, this is so-called the passive transformation. Now, the active transformation is you fix the coordinates are fixed. Let's say that you have some field, it has some value in this region, and what you do is you just translate that region. you shift your field, not the coordinate axis, but you shift your field. So what happens is now the shifted field, let's say, is phi prime at a given point. Let's say at that point, it has a value phi prime of x. But before being shifted, it was that point x was actually at the point x minus delta. So if you shift your field by delta, the new field with the same coordinate axis, its value at a given point will be the value of your original field at the unshifted position. So, you can have both points of view. They are both correct. Nothing, again, should not change. If I'm studying a system, choosing an axis at this corner, with origin at that corner, if I change my origin, physics shouldn't change. Or rather than doing my experiment on this table over here, I move my table over there and do my experiment without shifting my axis. Well, the physics should be the same. Nothing should change. This is what we mean by translational symmetry. Now, in general, what we will be looking at are systems, are cases in which we have a field phi, and we make a transformation on it. We obtain a new field phi prime of x, but we will be expecting our equations of motion resulting from d for x L of phi of x and d for x L of phi prime of x, the equations of motions should be the same. So we have two different Lagrangians in a sense. They should actually give me the same, I have the same form of the Lagrangian, but I change my fields in that form. And I will assume that I get the same equations both for phi and phi prime. Now, the only way to obtain this is, you see, here we are writing the action. How we obtain the equations of motion is by minimizing the action. But the action, the minimum of the action doesn't change if we just add a constant to it. A constant term is actually just the integral of a derivative. So if this condition is satisfied, well, that curly j, it can be some function, it can be 0. We will see both cases. If this is satisfied under our transformation, well, let me just move phi prime over here. Then we say that the system has a symmetry. Keep in mind that here I have phi of x at the point x. Here I have the phi prime, the new field, at the same point x.
Yeni terimin boundary'lerde zero olması gerekir.
No, it doesn't have to be. If that term, that additional term is 0 on the boundaries, then its contribution will be 0 to the action. But I can also have a constant contribution to the action. If it is not 0, it will give me a constant contribution to the action. And hence the minimum will not change. Well, let's see what this tells me. Well, we will be looking at continuous transformation. Noether's theorem is valid for continuous transformations, meaning that you can make very small transformations or very big transformations. But since you can also make very small transformations, I can say that phi prime of x will be actually phi of x plus some small variation of phi. I'm just considering a very small change in my field. Then this L of phi prime of x will be equal to L of phi plus delta phi. Now that is a very small change, so this will be equal to, now again, what will be our assumptions? We can assume that all the derivatives of phi are dependent on phi, or we can assume that the derivatives are independent of phi. It's up to us, but once we pick up a convention, we have to stick with it. I will assume that the derivatives and phi, they are independent. So now, so that essentially means that here is not just the phi, the argument of the Lagrangian, but also Lagrangian depends on the derivatives of phi. Well, now let's just make a Taylor expansion. By the way, before going on, just pay attention to one more thing over here. You see, we had these three different forms of the equations of motion, deriving the equations of motion, and I claim that they all give the same equation of motion at the end. You see, here, I'm writing this equation in terms of the action itself. Here, I'm writing this earlier Lagrangian equation in terms of the Lagrangian density. Here, I'm writing the Lagrangian in terms of, I'm writing this earlier Lagrangian equation in terms of the Lagrangian itself. So that will be an important distinction between all these things. It also is based on what are the assumptions. Well, let's go over here. Well, now I will be making a Taylor expansion, assuming the field and its derivatives are all independent of each other. So this is the derivative of the Lagrangian with respect to phi, delta phi, plus the derivative of the Lagrangian with respect to the derivatives of phi, times the variation of the derivatives of phi. But there I will also just change the derivation and the variation. This is equal to derivative of the Lagrangian with respect to phi delta phi plus the derivative of the whole thing minus del mu del L over del mu phi delta phi. Or let me just collect the first two terms. By the way, I am doing a Taylor expansion, so here there is an L of phi. But this is nothing but the equation of motion. So that is zero. That is the equation of motion consistent with the initial assumption I made, that the derivatives and the field itself are independent variables. So this is zero. So L of phi prime is actually L of phi plus del mu of this derivative, this term. But I also know that this is equal to, if this is a symmetry, you see, L prime, this first equality is always valid if the change in phi is small. It's always valid. If it is a symmetry, if that transformation that I consider is a symmetry, then we also have this second equality. But that tells me that del mu, derivative of the Lagrangian with respect to del mu of phi, del phi minus j mu is actually zero. but this is the equation of continuity. Which basically tells me that if I call this whole thing as normal J mu, then the integral of J0, if we call it Q, dq by dt, the time derivative is 0. Now, of course, it is 0 under the assumption that the fields, the J mu, goes to 0 at the infinity.
Neden J0'yu alıyoruz sadece?
Okay, you will see it when you see when you are doing the proof. Just think of the electric charge. You see, what is conserved? The charge, the integral of the charge density is conserved, not the current density. So what this equation of continuity tells us is that if we just consider a finite volume rather than the whole of the universe, any change in the total charge inside our volume will be due to the current flowing through the surface. So if you are considering all the universe, there shouldn't be any current out at the boundary of the universe. So the total charge inside the universe should be conserved. So this is like the integral of the density. That's why we are taking the 0 component. Okay, this is the essence of the Noether's theorem. So whenever you have a continuous symmetry, well, you see, we use the fact that it's a continuous symmetry by when we assume that when we consider the transformation of the field that is infinitesimal. If this is not a continuous symmetry, then you cannot assume that this transformation, there is an infinitesimal transformation. For example, parity, we will just send the x to minus x. I mean, there is no infinitesimal parity transformation. Either you make the transformation or you don't. But translation, you can consider an infinitesimal translation. And if it is a symmetry, Noether's theorem tells us that there is a conserved charge. There is a conserved quantity corresponding to that symmetry. And in the case of translation, that conserved quantity is what we call the linear momentum. Now let's drive the expression of the linear momentum then. You see what we did. What we need. Well, this is the current density. I need to determine how the field changes. Remember the definition of phi prime. Delta phi is phi prime of x was phi of x plus delta phi. That is how we define that delta phi. So we have to find this delta phi for a infinitesimal translation. And then we have to identify what J mu is corresponding to our Lagrangian. You see, the first property is independent of our Lagrangian. This curly J is dependent on our Lagrangian. So let's see. Phi prime of x, we said that if we take the active form, this should be phi of x minus delta. Infinitesimal transformation would just correspond to delta being infinitesimal. So this is phi of x minus delta mu del mu of phi. Of course, here I'm not just only considering space translations, I'm also considering translations in time. Delta 0 would just give me a translation in time. And still, I mean, whether I do an experiment now or tomorrow, the laws of nature should be the same. Okay, so, well, if this is correct, then I know what delta phi is. This is my delta phi. Okay, so I know how my field changes under translations. Now I should see how does the Lagrangian change under this transformation. Well, what was my Lagrangian? This was equal to del mu of phi squared minus 1 over 2 m squared phi squared. This is equal to 1 over 2 del mu of phi plus del mu of delta nu del nu of phi squared minus 1 over 2 m squared phi plus delta nu del mu of phi squared. Well, let me just keep the terms proportional to delta. I'm ignoring all the terms proportional to delta squared. So this tells me 1 over 2 del mu of phi squared. This is the square of this term. Minus 1 over 2 m squared phi squared. This is the square of the first term in the second line. This is my original Lagrangian. Then I have some mixed terms plus del mu of phi del mu of del nu of phi. This is from the first line. Minus m squared phi del nu of phi. So now the question is, those second two lines that we have, are they equal to the derivative of some other function? If it is a symmetry, you see, we had defined the transformation. Then the question is it a symmetry or not? Now that is what we need to answer. If it's a symmetry, then the change in the Lagrangian should be the total derivative of some other function. So let's try to organize it a bit. It is equal to del mu of phi times del nu of phi minus m squared phi del nu of phi. Or these two derivatives, I can actually change their order. This is equal to del nu. Well, you see here I have the del mu of phi and then multiply by the derivative of del mu of phi, but that is nothing but the del nu of the square of del mu of phi. Well, a similar thing happens in the last term. So it is minus del nu of 1 over 2 m squared phi. So this is actually del nu del nu of the Lagrangian. Or, if you like, I can write this as derivative with respect to mu. Yeah, okay, let me keep it derivative with respect to mu, del mu L, and this should be equal to del mu of this weird j mu. And this weird j mu is actually del mu of L. Now I have everything to use the Noether theorem. Well, the current density defined in Noether theorem, the conserved quantity, is that one. That is equal to L by del mu of phi. Well, the variation of the field was, well, this one. Okay, implicitly I change the sign of del in my derivation. So you see here del appears with the shift appears with a minus sign, but already here I just use the plus sign. So it's just delta goes to minus delta. It doesn't really make too much of a difference. Now I have to be a bit careful with the indices. You see this index mu and this index are different indices, so I should better give them different names. And this j mu is del mu L. Well, let me factor out this delta nu. Now, this is the quantity that is conserved. If I take the derivative, this total derivative with respect to x mu, it will be 0. But remember, delta nu is arbitrary. I can choose, well, it's arbitrary. I can choose the shift in any direction I want. It should still be a symmetry. As long as delta is small, this will be my current. Well, that basically tells me that rather than having one conserved quantity, now I have 4 of them, corresponding to translations in each one of space and time. And so let me define this T mu nu. This will be derivative of the Lagrangian with respect to del mu phi, del nu phi, minus g mu nu. Let me also be consistent with my upper and lower indices, minus g mu nu of L. And what we know is del mu T mu nu is equal to 0, which tells me that the conserved quantities are actually these ones, d cubed x T0 nu. And since the nu is kind of free, you see it corresponds to the direction of my shift in the symmetry. I actually have 4 conserved quantities here, not just 1. Now let me just call it P nu. Why P? Well, this is a conserved quantity which corresponds to translations, and we know that that is actually the momentum. Well, what about the 0 component? It should be if this is the energy momentum vector, conserved energy momentum vector, the 0 component should be the Hamiltonian. Well, let's look at the 0 component. P0 is d cubed x. Well, T0 nu is del L by del 0 phi. del 0 phi minus L. Well, if del 0 phi is nothing but phi dot, and this is nothing but the canonical momentum conjugate to the coordinate phi. So P0 is d cubed x pi of x phi dot of x minus the Lagrangian. Well, this is the expression we used to obtain the Hamiltonian last week. So we don't need to repeat that, but we will look at the three components. What about the Pi? What will be their form in terms of our creation and annihilation operators? Any questions up to here?
What is the difference between the pi and pi?
Okay, nice question. That was one thing I was hoping you would ask. You say one is the conjugate momenta. It's just a, in a sense, abstract concept. The other one is the linear momenta that you call the motion, the translation, etc. They have nothing to do with each other. Almost nothing to do, let's say. Depending on what is your generalized coordinate, it might actually correspond, the generalized momentum might correspond to your linear momentum, but it doesn't have to be. Linear momentum and these generalized momenta are completely different things. Okay, let's give a 10-minute break. We will start in 11:15.